To the master video of how to quantify our samples, whether you're imaging for ionic liquids, the KCC2 project, or a completely new project. This is an all-encompassing video on how to standardize, how to compress your image, and how to go about quantifying. So to start, I have created a master folder called the Ionic Liquids Quantification folder. It should be on this zebrafish flash drive, although you may be accessing it in a different way. I don't know. This video is being made in 2025. A lot of things could have changed from when you're watching it. So at least within this folder that I've created, I have included 4 major things that you need in order to quantify. The first thing is this Fiji application. Fiji, formerly known as ImageJ, is the software that we use for quantifying all of our images. If you don't get it from this folder, it's as easy as going to Google and looking up Fiji ImageJ download. And even the first link should be appropriate for downloading it, whether you have Mac or Windows or whatever software you're working from. Now the next thing we use is this application called Free Ruler. I'm on the Mac, and that's how I was able to find it, but it should be available on multiple devices. As you see, as soon as I launch it, it just gives me this ruler that counts up to 800. I think this is pixels. So this is a very simple, very easy apparatus. And then the very last folders that are important are one for the spinal cord and one for the puncta. Now, the spinal cord folder has this image that I've created, which is a guide on where I quantify the spinal cord, and I'll run through how I go about this with an image soon. But you'll see that I've divided the image into theoretical fifths, which you can imagine will be done using the ruler. And then I usually use 2 pre-made tools in order to measure either in the spinal cord or the background that we're going to subtract. And you'll see the tool for the spinal cord will be a little bit bigger than the background. Now, where are these tools? They are all pre-made. This one's the background tool, and this one's the spinal cord tool. Now, you won't be able to see the shape of them until you're in the actual ImageJ or Fiji software. Now, the only other thing in here is a document called parameters. These are the standardizing settings that we use so that all of the images that we're looking at are on the same exact settings, so that all of the data that we're collecting isn't varied depending on a different fluorescence value because of an overexposed or underexposed image. So you'll see for the spinal cord, we usually condense it into something called the sum of slices. Then we take a lower bound of this number and an upper bound of this number, and I'll show you guys where to plug these in. Now, this is the same exact thing for the puncta. So you'll see we have a parameters doc with different values, and that's because the puncta tend to be a little less exposed than the actual spinal cord. Then you see we have a background tool, we have a puncta tool, and then we have a second demo image that shows you that instead of dividing the image into separate sections and measuring in the middle, we focus on this specific area here. Now, this area has worked for our project. This is subject to change depending on what project you're working on, so obviously take this step with a grain of salt depending on your situation. So now let's launch into how to use these tools and how to use ImageJ in general when it comes to quantifying, standardizing, and preparing your images. So before we begin any of that, you want to make sure you have a document set up for collecting your data. So let's just launch any spreadsheet, and I'll show you guys how to set this up once we actually open the software. So now I'm going to open up my Fiji software, so we'll go back here, we'll go to the zebrafish folder, and we'll open up Fiji. And once Fiji launches, you're going to see that it has one major aspect that you're going to be working off of. So let's just give it a second. So this is that major aspect that we're working off of. Fiji is basically a toolbar. You want to navigate it based off of this, and then obviously the menu at the top of your window. So what I'm going to do is I'm just going to adjust the recording settings of the screen so that you can see what I'm doing at the top window as well. This toolbar here that I'm working with, but I also have this bar up here, which is very important for navigating Fiji. So I'm just going to show you guys how to do this based off of one random image. So we'll start off by going to File, Open, and I'm going to open up some of the data from the Ionic Liquids project that I've been working on. So we'll go to that folder. And let's do one of the 7-day controls because these guys should be more developed, and since they're not an experimental group, we should be able to see the puncta and the spinal cord a little bit better. So you'll see it'll open up the file and we have both the unprocessed and the processed images. I'm just going to scroll down and see if I can find one that I like a bit more than the rest to use for this demonstration. Okay, so as you see, the file's open, and usually it's going to open up however many windows in which you imaged your sample. Now, we imaged the sample with 2 different windows, and I'm interested more so in the green one, which stained for a synaptic marker. I'm not interested in the red one, so I'm just going to X out of that one. So before we do anything with this image, I want you to note that there is a slider at the bottom. This allows us to move through all of the slices of the image, showing us the stack instead of one condensed image. Now, when we quantify, we want to quantify the entire image condensed together so that we're getting information from everything from top to bottom. Now, before we condense it, we need to make sure that everything that's being condensed together is something of value. So in this case, I'm quantifying the spinal cord, right? I want to make sure that all of the images that I'm condensing into this sum are images that are going to give me a clear reading of each part. So something I'm going to do is I'm going to go to Image, Adjust, Brightness and Contrast, and I'm going to adjust the brightness and contrast of this image until I get a clear shot of what I'm working with. So I'm just going to play around with this. It doesn't have to be perfect. And since I'm focusing, you know what, since I want to show you guys the puncta and the spinal cord, I'm going to make these adjustments with both of them taken into account. So now I'm going to move the slider, and I'm just going to look at this image and see, is every aspect of this image a good place to quantify from? Or is there a point in time where an area gets kind of muddy and it's not worth quantifying? So this image looks okay. An example of when it would get muddy would be if, for example, you see how when I drag it all the way here, it gets kind of blurry? Something I can do is I can note the earliest time in which it begins to get blurry. So it looks like it's pretty solid until maybe like 30. Let's say 30 to be safe. So when I stack this image, I'm only going to stack it from 1 to 30 of the stack instead of going the whole 67 because we're losing a lot of important data in that area once we go too far. So let's say I'm following these parameters. The very first thing we're going to do is reset it back to what it was. And now we're going to go to Image, Stacks, Z Project, and we're going to make it a sum of slices as far as we said. So I said 30 in this case, so let's sum it. Now we have our stack. So the next thing we're going to do is we're going to set it based on the parameters. So the parameters for the spinal cord were a lower bound of 33344 and an upper bound of 232757. So let's go over here. We're going to go to Image, Adjust, Brightness and Contrast, and we're going to click Set. Now we put these values in, 33344, and the other ones were 232757. So 232757, we're going to apply it, and you'll see that we lost the puncta. That's because this standardization is specifically for the spinal cord. That's also why we have 2 different ones and we don't use the same standardization for both. So now that I've standardized it to be what it has to be, the next step is going to be taking our ruler. So now we can go back to this folder and open up our ruler tool. And we're going to divide this image into fifths. So you'll see that this ruler measures the screen up to about 681. We could say about 680 to be round. And if we divide 680 by 5, we know that we're doing 136 size sections for each part. So we'll go to our marker or our brush tool. We're going to go to the value that we said, and we're going to keep marking every time we get to that value in order to make 5 even sections. Now, for the sake of this video, I'm just going to eyeball it, but you would ideally keep going up in increments until you get 5 even sections across the image. Now, let's cross-reference my folder one more time. Once you create these sections, you're measuring in 2 areas. The first measurement you're doing is with the spinal cord tool, and that's to get 5 parts in the middle of each section. And then you're going to do the same thing with the background tool underneath in the area of the fish. So now that we've split this into 5 and we've gone over our reference image, we're ready to quantify using our tools. So we're going to open these by going to Analyze, Tools, and ROI Manager. From here, we're going to click More, Open, and now we can open up those tools that we have. So for the spinal cord, we're going to open Spinal Cord Tool, and we're also going to open Background Tool. So to start with the Spinal Cord tool, and make sure you go back into one of these tool selections, because if you keep your mouse the way it is, it's still going to draw. So we'll go and collect this one, maybe with a rectangle, and now we can move the tool around. And just as we said, we're going to start in the middle of the selection area, go down to the middle of the spinal cord, and then you're going to click Command M. And once you do that, you're going to get the only two values that we really care about, which are the area and the mean. And I'll explain why in a second. So you're just going to keep going down to the middle of the section, measure. So now I've done my 5 measurements for the spinal cord, and I'm just going to document these measurements so that we have them and we know what they are. So I'll go back to this here, I'll paste them in, and let's just call this spinal cord 1 for now. I'm going to make sure I know what these are. So we've established that these are the area and the mean. So area, mean. Now we're going to do the same thing for the background. So I'm going to create another area, call it background. I know we're going to have the area and we're going to have the mean. So let's open up Fiji again. I'm going to delete these values, and now I'm going to take proper measurements. Let's get the background tool in there, and let's do the same thing. So before I measure it, I just want to show you guys. I know I'm measuring from the inside of the fish. So make sure you, if you have to, reset the brightness and contrast so that you see that you're measuring from the inside instead of some random outside portion. Something I like to do is I like to first notice where the inside of the fish is and then just keep this background tool very close to the spinal cord so I know I'm always getting it exactly where it has to be. You also want to make sure you're avoiding these white parts because these are considered puncta that can throw off your measurement. So something I'll do sometimes is I'll amp up the brightness and contrast just like this so that I know exactly where I should go. That's not going to get any random measurements. Then I will reset it to what it was before. And then I'll get my measurement. Do the same thing. So reset it so I know exactly what area I'm getting my measurement from. So somewhere like here looks like, or even here is better. Looks like we're not getting any kind of puncta in there. Set it to what it has to be. And measure. And you're going to do the same thing all the way across. Now for the sake of efficiency, I'm not going to keep resetting it just to get some like values that I can show you guys. So let me just get 5 values. Now we're going to copy these and we're going to paste them into our document. Okay, so right now we're in an old document I have of data that I've collected for my project to show you guys how this document can look when you set it up. So as you can see, I have a bunch of sections per sample. So sample 1, for example, has sections A through E, and I get the area for them, which should all be the same because you're using the same size tool. I get a mean value for them, and then we have this third section called integrated density. Now integrated density is just a way to account for how much fluorescence value you're getting in a certain area, so you multiply the two. So for the actual data that we're getting from the spinal cord, integrated density is simply the mean times the area. So we'll go to this document that you should have made. We'll put integrated density here, and we're setting up a function that is just the area times the mean. And we can just drag that down. It should be the same for all of them. Now the background is a little bit different. The background integrated density formula is the mean of the background times the area of the actual spinal cord shape. And that's because we want to make sure that the fluorescence value we're getting is accounting for the size that we use for the actual data, not the smaller size that we use for the background. That makes it a lot even and makes our further calculations a little bit more organized. So integrated density for the background is going to be the fluorescence of the background times the shape that we used for the actual quantification. So we'll come over here, make a section for the background, and let me actually separate these so it's a little bit easier for you to follow. And the formula for this is the mean of the background times the area that we used to do our actual quantifications. And we travel that all the way down. So now we have all of these values that we've gathered, but what we care about the most is something called the CTCF. And CTCF, or the corrected total cell fluorescence, tells us how much fluorescence we're actually getting from the spinal cord when there is no background taken into account. So that's the information that we actually care about. Now, how do we calculate CTCF? CTCF is the integrated density of our actual sample minus the area of the sample times the background mean average. So how does that translate to this data here? Let's break it down a little bit. First thing we're going to do is let's get an average value for each of these so that we're not dealing with a bunch of these random values. So I'm just going to do average of integrated density here. So here we took the average of the integrated density. For the background, we're going to do the average of the mean. So this is actually going to be this. Our CTCF is the integrated density of the sample minus the area size of the sample times the background mean, aka the integrated density of the sample minus the integrated density of the background. So we either do it as the breakdown, which is the integrated density of the sample minus the area of the sample times the background mean, and that should be the same as doing the integrated density of the sample minus this value, which is going to be the average of the integrated density. And we see these are exactly the same. So if we go back to my old document, you'll see I've done this for practically every single sample in the section. So there's 12 samples, so I take 5 averages per each sample. Eventually I get the mean values over here, and that makes it easier for me to calculate my CTCFs. Then I end up doing statistical analysis, which you'll learn in your RDA class or any other math class that you're taking. So doing the puncta is very similar, just as I showed you before. The only differences are that for the puncta, instead of using this ruler tool, you're just measuring the area of interest, whether it's this area or somewhere else you've determined, and you're using different tools for the puncta as well as different parameters. Otherwise, that's pretty much how you do your quantification. Hopefully this all makes sense, and I wish you the best of luck in this very tedious but rewarding process.